Softmax regression. The logistic regression model can actually be extended to support classifying multiple models directly, right? So eliminating the need to train and combine multiple binary classifiers like one versus all and one versus one. So that's called softmax regression. Sometimes multinomial logistic regression is another term that's used. So the principle is pretty simple, that given theta, the softmax regression just tries to calculate a score, sk of theta, for each class, where k is the class, right? K is the class, and s is the score, given your parameter theta. And subsequently estimate the probability of each class by applying the softmax function, also known as like a normalized exponential to the scores. So it looks very similar in that our basic equation now is sk of x is equal to x transpose theta for a particular class k. Note that each class poses its dedicated parameter theta k, typically stored as rows in a much larger theta, like a capital theta matrix. Let's see if I can draw out like a capital theta. Kind of looks like that. That is the world's worst capital theta, but you get the idea. So once you've kind of computed the scores for every class for the instance, the model can estimate the probability pk hat, right? Because it's an estimated probability. The hat means that it's estimated, which is equal to sigmoid of our score of our data x for a particular class, which is equal to the exponential exp of sk of a particular class over the sum of k j equals 1 exp of sj of x like that. So in this sense, right, k is the number of classes, s of x is a vector containing all the scores. Of x, right? Or x for a particular, let's say of x for a particular instance. And then sigmoid s of x, right, signifies the estimated probability that the instance x of I belongs to a class k, or however many classes that you're trying to classify it as, right? So Virginsia, Ceratosa, things like that. So similar to logistic regression, the softmax regression classifier predicts the class with the highest probability corresponding to the highest score. Another way that you can write this to be more compact is that you can say y hat is equal to arg max of sigma. Oops, sorry. Arg max of sigma time of s of x of k argmax for a particular class k. You can also write that as, so to clean up some of the math that you saw before, argmax of s of k of x. So if we put the subscript there on S of k, then we're assuming that that has the sigmoid activation function already included in it. And that's how you'll see it in a lot of places. And I believe different places have it different ways. So I just wanted to share it both ways. It was confusing when I was trying to put this together. And then the last way you can see it, which you'll never really see in anything other than academic papers, might be argmax of k, and it's max, is equal to parentheses theta of k. So our parameter is k transpose times x. Again, probably overly complicated and not really needed a whole lot. So again, the argmax operator, if that's not familiar to you, identifies the value of a variable, in this case k, that minimizes a function. So in this context, it returns the k that minimizes the estimated probability of sigma s of x subset k, or subscript k. So now that we have a basic equation, we need what we always need, which is a cost function, right? We need something that's got j on the left side. However, now we have multiple classes, so it's going to be j of capital theta. Oh, it looks a bit better. And that's going to equal to negative 1 over m. Again, negative because we're looking downhill, gradient descent. Summation of I equals 1 to m. And summation of k equals 1 to k, because now we have multiple classes. And that's going to be y of k to the I log of p delta k subscript of I and that in that equation, right, yk of I takes the value of 1 if the target for the ith class belongs to k, otherwise it takes 0, this one here. So 1 if the ith target belongs is in k, and 0 elsewise. And that's going to be what allows us to train that. If we want to actually calculate our gradients, we can do that by just expanding that out for the cost entropy cost function, the cross entropy cost function. In our gradient of our parameter theta for a given class k, multiplied by our cost function for all of our data, j, that actually simplifies down to a much easier equation than one would think, which is just 1 over m summation of I equals 1 to m of p hat k of I minus y k of I x of I. So that enables the computation of a gradient vector for every class, thus kind of facilitating the utilization of gradient descent or any other optimization algorithm to determine the parameters of theta, capital theta, for our entire class, right? So we can apply softmax regression to the iris flowers for all 3 flowers, and we can do that setting scikit-learn's logistic regression to default, or 1 versus all for more than 2 classes. So you can also just set it in softmax regression by setting hyperparameter. So you want to set the, when you're doing softmax regression, okay, set the hyperparameter multiclass equal to multinominal. Okay, so that's going to hide all the math from you, but that's going to create a multinominal data set. So there's a number of linearization that takes place within the data set, within that algorithm that we won't discuss too much right now. But this is what we get if we do a multinominal logistic regression. And for petal length and petal width, we can get 3 different classes. And there is a little discrepancy here. Don't mind the triangle of confusion, but we can get a 0.5 classifier if you want a nice 50% classifier, just as before. And so we can easily separate Certosa from versicolor. And then we've got pretty much the same classifier that we've got up here, right? Which is separating Virginsia from versicolor. You can also adjust this regularization by adjusting the hyperparameter C. So adjust or change C to adjust your L2 regularization. And that might determine how close it wants to cut things, right? So I think if we do it here, it will definitely affect kind of this part of the plot. But it really doesn't matter too much how you're classifying out there because we don't have any data out there. It's always dangerous to say I have a new data point that shows up here and I'm classified as 90% not Virginsia, but it's probably like a caterpillar, not even a flower, right? Petal width, it's a very wide petal. That is a petal that is wider than it is shorter. You probably just measured it the wrong way.